This is part 2. We're doing some notes and progress check 2.11. So one thing I want to note in this section is that you have known sets most of your life. It's just that we're learning the language of sets in this section. So when you learned how to count and someone showed you, like the sort of the picture books that I have teaching my kids to count with, there'll be like 2 owls. It's like, how many owls are there? 1, 2. You counted the set of owls. And then it shows 3 cars. How many cars are there? Well, there's a set of 3 cars, and there's the size of that set is 3. The set of cars and size is 3. And so this language of sets you've known all your life. You've known about sets all your life, but you haven't known the language of sets all your life. And so this is where you just need to be thinking about. This is like if you were in like a second grade math course in French. It's going to be, the language is going to be totally different, but you should be able to catch up on the things that you already know. So be aware of the things you already know when you're going through this section. So here's an example. So let's say S is the set of numbers 1, 4, 7, 10, so on and so forth. And T is a set 2, 4, 8, 16, so on and so forth. So let's find 4 more elements in each set other than the 4 used that satisfy the roster method. So this is called, the author of our book calls this the roster method, because it's kind of like if you were going to a sports game and you'd looked at the different players who are on the team, it'd be like a list roster. So in this case, and then we use the ... whenever the pattern continues. So here, S, what's the pattern in S? Everything's going up by 3. So the next numbers will be 13 and 16 and 19 and 22. And then what's the pattern in T? Well, it's doubling. So then you're going 32, 64, 128, 256, and so on and so forth. So there's 4 more numbers added. One definition that I want to go over is that sets are equal when they have precisely the same elements. In this case, we write A equals B. If the sets C and D are not equal, we write C is not equal to D. Now, this works. We're using the same symbol that we use with algebra with numbers, but you just need to be aware that this can be really different, because in order to show that 2 sets are equal, you're going to have to show that everything in A is actually in B, everything in B is actually in A. And so it's like a 2-step thing to show equality with sets, whereas with numbers, you just kind of do some algebra. Okay, a variable is a symbol representing an unspecified object that can be chosen from a given set U, which is called the universal set for the variable. So a constant is a specific member of the universal set. And then our book uses the word predicate for a sentence where you have undetermined variables, but open sentence is actually what most people use now. Predicate's still in fairly good use, but open sentence might be more common now. So just be aware of that. If you catch me saying open sentence, I should have said predicate, but they mean the same thing. So for instance, here we've got the universal set for all variables is the integers. And so let P of X be the predicate, X squared is less than or equal to 4. So this is not a statement, but it's a predicate, because if you plug in a number for X, it becomes a statement. So find 2 values of X for which P of X is false. Well, 3 and 4 are values where it's false, because 3 and 4 give you 3 squared is 9, 4 squared is 16. Those are too big. Find 2 values of X for which P of X is true. Well, 0 is true for 0. It's also true for -1. So if -1 squared would be 1, which works. Let's use the roster method to specify the set of all X for which P of X is true. Okay, well, we've got numbers that it works with are -2, -1, 0, 1, 2. And you don't have to put them in order, because order doesn't matter with sets. But those are the integers that work with that have a truth value for that predicate. Assume the universal set for all variables is z and let r of x, y, z be the predicate. X squared plus y squared equals z squared. Find two values of x. Oh, I should have said x, y, and z, for which it's false. Well, 0, 0, 1, that's false. 0, 0, 2, that's false. You can go on forever like that. Two values of x for which x, y, and z for which it's true. Well, this is, might recognize this as Pythagorean theorem. And so it's any three numbers you find are what's called a Pythagorean triple. So for instance, 3, 4, and 5 work, where 3 squared is 9, 4 squared is 16, 9 plus 16 is 25, is 5 squared. Another example might be 12 and 5 and 13. So 12 squared is 144, plus 5 squared is plus 25, so 24. 144 plus 25 is 169, which is 13 squared. It's always useful to have a few Pythagorean triples memorized. Okay, truth set of the predicate with one variable is the collection of objects in the universal set that can be substituted for the variable to make the predicate a true statement. So, I'll just keep going. We're doing a couple progress checks right now. Just got so excited, just kept moving before I was supposed to stop. All right, so if the universal set, so p of x is a predicate, x squared is less equal to 9. If the universal set is the real numbers, what is the truth set using English and using set builder notation? Okay, so in English, it would be real numbers between -3 and 3 inclusive, meaning including the endpoints. Okay, and then set builder notation might be -3. No, I need x in R. If I were in Microsoft Word, the /in would have turned into the right symbol. -3 less than or equal to x less than or equal to 3. So forgive my my lack of being of good notation with Zoom. So this would be the symbol for in, which looks like a backwards 3, a little bit smaller though. This would be the less than or equal to with like the little arrow, a little line underneath it. Okay. If the universal set is z, what is the truth set? Well, it's the integers between -3 and 3 inclusive, which would be the roster method would be like -3, -2, -1, 0. Well, let's just write it down. So integers between -3 and 3 inclusive. So another way to write it would be -3, -2, -1, 0, 1, 2, and 3. Okay. And then are the truth sets of 1 and 2 equal? No. So this one right here is missing all the numbers between 0 and 1, for instance. So 1/2. It's missing pi over 2. It's missing the square root of 2. It's missing all fractions that are not integers. It's missing all the irrational numbers in between -3 and 3. So not equal. So that finishes our part 2 video.